the experimental determination of the heat of combustion reactions is typically done at constant volume. Now, that container that is used for this experiment is called a bomb, so this procedure is known as bomb calorimetry. Okay? Now, when you're doing bomb calorimetry, the heat of reaction is not going to be equal to delta H. Okay? It's going to be equal to delta E. And the reason for that is this. Remember the first law, delta E equals Q plus W? Well, at constant volume, okay, remember W is what? Minus P delta V, right? So at constant volume, this W here is going to be equal to 0. Delta V is going to be equal to 0, right? So Q then will just be equal to delta E for a bomb calorimetry experiment. So your heat of reaction will not give you delta H, it will give you instead delta E. So how are you going to determine delta H from delta E? Well, you go back to the definition of H. H is U plus PV. So delta H would be delta U plus delta PV. Okay? So that means if I can figure out delta U, okay, this is going to be, I'm sorry, E plus PV. U, by the way, you might see that instead of E, because in upper level classes like physical chemistry we use, or in physics classes they use the letter U. Okay, so let me fix that. It should be E plus PV. So delta E plus delta PV. So delta E you can determine from bomb calorimetry. From bomb calorimetry data. You just have to apply a correction term to that, delta PV, in order to get the value of the delta H. Now, pretty much the change in the pressure here, the volume doesn't change, right? So it's the change in PV value will be due to the change in the pressure. And so the reason the pressure changes inside a bomb is because the reaction produces gas. So the change in pressure will be primarily due to a change in the number of moles of gas in the container. So if we assume the ideal gas equation, you say PV equals nRT, the change in PV is going to be equal to delta of nRT. Now, since in our thermochemical, when we write our thermochemical equation, we're assuming we're looking at the delta H going from reactants at some temperature, usually room temperature, 298 Kelvin, and we end up with products at the same temperature, okay, for that delta H. Then this T right here is a constant. Of course, you know R is a constant, so the only thing that can change here is N. So this is N gas, okay, moles of gas. So that's going to be delta N gas times RT. So this is the formula that you'll use to get the delta H from bomb calorimetry data. You have the heat of reaction, which is delta E, and then you add delta N gas times RT for that. Okay? So here's an example. Let's estimate the delta H for this reaction. If we measure the delta E, let's say we found the delta E from bomb calorimetry to be equal to X for this reaction. You have combustion of methane. So methane plus oxygen gives you carbon dioxide gas plus water liquid. Well, let's see, what was our formula? Delta H equals delta E plus delta PV, or delta E, which is going to be X, right? Plus our delta PV is delta N gas times RT. Well, for X amount of energy here, delta N gas is how much? Well, delta N gas is moles of gas on the product side. What do we have? We have 1 mole of CO2 gas. That's liquid, so that doesn't count. And so delta N gas in this case is 1 on the product side, minus on the reactant side you have 2 plus 1. So 1 plus 2, 1 minus 3, that will give you negative 2. So that means delta H is going to be equal to delta E, which is X, plus delta N gas, which is negative 2, times RT. And the correct answer here is B.